So now let's start discussion of tensor calculus. So we'll start by setting the rules of the game. That's what chapter 2 is called, the rules of the game, where everything's taking place. You have to have a starting point. You have to start somewhere with some concepts that are accepted as obvious or natural. So for us, that concept will be the concept of space. Everything's happening in the space of our common physical experience. We call it the Euclidean space, without much definition. So we all have an intuitive understanding of what our space is and what we can do with space. What we can do with space is basically what Euclid did with geometry. You can draw straight lines, you can draw planes, you can draw circles, you can talk about distances. We'll do that in a moment. And we'll also talk about the quote-unquote two-dimensional space, the plane. We also understand what the plane is. It's something where you can draw straight lines. All of these are called Euclidean spaces. That's what we're calling Euclidean spaces. What we agree on is the space of our everyday physical experience, where it is possible to draw straight lines and measure their lengths. So I'll just give you an example of something that's not a Euclidean space. The surface of a sphere, because we're not able to draw straight lines, I would not call a Euclidean space. That's a space without straight lines. You can still measure curved distances, but it's different. So some features are very much the same because you have curves and they have lengths. So you're in business for calculating lots of things, but it's just not the same. You cannot draw straight lines. In a moment you'll see that being able to draw straight lines is equivalent to being able to draw and use a Cartesian coordinate system. We never will use it except when it's really called for, but the possibility of having a Cartesian coordinate system is kind of an important thing to keep in the back of your mind. So we're in this space. We also start with the concept of distance. And it's very important to understand that distance exists on its own terms. So we will say, I'm calling these pieces of chalk to define a unit of distance. So we'll call this our unit of distance. It will allow us to calculate areas of squares and rectangles and volumes of cubes and rectangular shapes, but also other shapes like tetrahedra and even curved shapes. So we'll say that the volume of a sphere is a non-controversial concept. We all understand what the volume of a sphere is without having to define it. It's how much water you can pour into it. And if you were to pour water out of it into a cubic shape, into a rectangular shape, we could put marks on it and see how much water we poured out. We would call that the volume of sphere. We also understand what the surface area of a curved shape is. So in this course we won't struggle with defining those areas. Actually defining them precisely in the modern formal sense has proven somewhat difficult. But without having to define those concepts, we can just use them as intuitively clear. They would be our fundamental concepts. What we will focus on is how to work with those concepts and how to measure them. So that's the space we're in. What can we do with the space? Well, we can define functions. It's very important that we're defining functions of space. So in this room, we can talk about temperature as a function of a point in this room. So I can take a thermometer and measure temperature at this point and then assign the particular temperature to this point. That's the temperature at this point. I don't need to introduce a coordinate system for that. I'm bringing up a coordinate system by saying that we don't need it, but I wouldn't have to really bring it up. I could say at this point we have a certain temperature, there it is. At another point you might have another temperature. So our functions initially are just functions of space. Right? We distinguish among points and we say at a certain point the function has a certain value. So that's nice. That was a scalar function. Because we live in a Euclidean space and we can have straight lines, another fundamental concept will be a vector. One of the most fundamental vectors is the position vector. Let's limit ourselves to the plane. pick an arbitrary point that we, for lack of a better word, better term, we'll call it origin. And then to every point in the Euclidean space, draw a vector from that point. So here's another point. Here's another vector. We're going to call this the vector R. In the book, it's denoted by bold letters. On the blackboard, I'll just put little vector signs over them. These are vector quantities. What's a vector? It's a segment with a direction. So at every point, there could be a vector, and that would be a vector function. So a vector function could look like this. So at this point, it's this vector. At this point, it's this vector. At this point, it's this vector, and so forth. At each point, there is a vector. So that would be called a vector valued function. Let me go back and repeat what a vector is. A vector, and I'll emphasize this over and over again, is a directed segment. It is not a pair of numbers. It would be to your great detriment to think of vectors as pairs of numbers. Or if you're coming from linear algebra, to think that there is some sort of universal basis with respect to which these vectors are decomposed. None of that. You have to accept these objects on their own terms. These are directed segments. They're beautiful objects. You can add them, you can multiply them by numbers, in other words, you can form linear combinations. More importantly, it's not new from what I just said, but you can subtract one from the other. They're beautiful objects, even though they're basically pictures. They are just pictures. They are these things that I've drawn, nothing more, nothing less. That's what they are. And you're used to, you know, not in my linear algebra class, but in some linear algebra classes, probably most, to immediately think of them as a pair of numbers, or in the three-dimensional space, as a triplet of numbers, and so forth. Don't do that here. They're just vectors, and you can add them, not like they were numbers, you can add them in their own right. Vectors can be added by the parallelogram rule. They can also be subtracted. That's not different from addition. You just multiply it by a negative number and subtract it. So if you can subtract things, you can take derivatives of them. We'll discuss it in just a second. But all sorts of things that you can do with vectors. You can do just about everything you want to do. You can do with vectors. Most interestingly, you can take derivatives of vectors. If you have a vector as a function of a parameter, so v, it's not even important at what point in space it is, but if you have a vector v as a function of some parameter alpha, you can take the derivative of v with respect to alpha. That's a preview. We'll do that in a moment. The vector to which the operation of the derivative is most commonly applied is the position vector. You can see why it's called the position. Sometimes it's called the radius vector. All of these kind of make sense, right? But it basically tells you the position of the point. And at this point, so at this point, this is the position vector. So it would be more accurately to draw it like this, starting at this point. But this is a better way of visualizing it. Vectors have length. Why do vectors have length? Because the Euclidean space gives you length. I can calculate the length of any vector if I have the unit vector. For example, this one is 0.9. No units. It chalks. Right? No units. This one is 0.75. This one, hey, that's 1.1. I hope I have a unit vector somewhere. I don't. I'm going to draw one. There you go. There's a vector of unit length. Right? So Euclidean spaces give us length, so we can measure lengths of vectors. Before I talk about the differentiation, I will define another very important operation on vectors, the dot product, and highlight the difference between this approach, really the approach of vector calculus and physics, from the linear algebra approach. So, U dotted with V. U, capital U. I guess we'll stick to capital letters, just like we do in the book. U dotted with V is by definition the length of U. times the length of v times the cosine of the angle between them. Familiar from physics? But it's very important to have a starting point and then go from starting point. Our starting point was the concept of length. Because we're in a Euclidean space, we can use all of the Euclidean concepts like angle. So we have lengths, we have angles for free. They're our primary concepts. If we have those two concepts, we can multiply one length by another and the cosine of the angle between them. And that, for better or worse, is our definition of the dot product. Right? From linear algebra, you probably remember why it's such a useful combination. It just happens to be a super useful combination. The most super useful aspect of this operation is that if you dot a vector with itself, you get its length squared. That's the number one thing to remember. Dotting a vector with itself is its length squared. And it's linear in each operator. So u1 plus u2 dotted with v is u1 dotted with v plus u2 dotted with v. So it's linear in each argument. And again, and I think behind the scenes, the most important thing here is that we're using our primary concepts of length and angle, geometric objects. So we've started with Euclidean spaces with lengths and angles. That's all. That's all the elements in addition to numbers that we'll have. There will be no new concepts. There's volume and area, but we take those for granted. Okay. One very important thing that I wanted to mention, and I forget what it is. What did I want to mention about this? Okay, it'll come back to me. Okay, so that's the dot product. Now let's talk about differentiating vectors. So let's look at v of alpha. So one good example is, suppose at one moment, let this be v of 1. V of 1. And let me draw, still breaking in this chalk, v of 2. I'll just say what it is. Let this be v of 2. Let this be v of 1.5. Let this be v of 1.25. And so forth. So I can without writing, I can say that the limit of v of alpha as alpha approaches 1 is this vector. Does that make sense? This was 2, 1.5, 1.25, 1 1/8. Did you see how I chose them? That's just one example that I chose. So, look, when you heard the word limit, you're used to seeing numbers. Limit of a function, limit of a sequence. Right? But vectors, because you can talk about the distance between two vectors, the difference between two vectors, and how small it is, right? Because you have the length of the difference. Right? So that's all you need to talk about limits. So vectors, even though they're just pictures, but the concept of limit extends to vectors as pictures perfectly. Think of these vectors as directed segments. Don't ever imagine a background coordinate system or a basis to help decompose these vectors and turn them into numbers. Don't turn them into numbers. Don't think of them, well, I can make sense of the limit if I think of a vector as a pair of numbers. And if I think of a vector as a pair of numbers, then I really understand what the limit means. You don't need to go through that step. You can just see that this arrow approaches this arrow. And then you can also talk about the derivative. And the derivative, so I will write v prime at time t at time 1, just to go with that example, is the limit as some small number approaches 0 of v at time 1 plus h subtracted v at time 1 divided by h. Sorry, I'm still breaking in this chop. It'll get better. Do you remember this as the definition of the derivative? And do you realize that all the elements of this expression, you can do all of these things with vectors? Can you look at v, take a small h, like 1/4. V of 1 plus h, can you quote unquote evaluate it, which means look at it? And yeah, sure you can, here it is. And can you subtract from it v1, v of 1? Yeah, sure, you can subtract vectors from each other. Let me draw the difference. Here it is. Here's the difference. Maybe I should draw it at this point, but it doesn't matter. We're just talking about vectors, not the point they're at. But just, and can I then divide it by h? Sure you can. Right? So you can do all of this. And each time you, well, let me divide it by h. H was 1/4 in this case, so divided by h, it'll be this one. So I have, what I just drew, the last thing I drew was the vector, this expression for h equals 1/4. And then can I take the limit as h goes to 0? Yes, you can, because you can take limits with these pictures. And you would probably get, 1/4 is already very small, you will probably get a vector that kind of looks like this. So, yes, you can very much take derivatives of vectors. If you have a vector as a function of a parameter, it just takes a moment to get used to it. And a lot of reinforcing that vectors are vectors and not pairs of numbers. It's a sort of undoing the damage, quote unquote damage, you've done before, where there's this irresistible force to forget about geometry as quickly as possible and go to algebra as quickly as possible and forget where geometry came from. So undo that a little bit. Do all of these things with vectors. So vectors can be added together, subtracted, all of that is basic. Dot product, that's something very specific to vectors. A very nice operation. And then we can also take derivatives of vectors. These are all parts of the rule. We'll be taking derivatives of vectors all the time. All the time. We'll take derivatives of vectors. So in the book, I have this example. I literally had v of alpha so it was on this circle. Right. V of alpha just going around in a circle. And it was the unit circle. And there was a short discussion that used a little bit of trigonometry, but it showed that the derivative, so if we call this v of alpha, where alpha is literally the angle with some arbitrarily chosen line, then the derivative v prime of alpha was a vector orthogonal to v of alpha and of the same length. In our example, it was of unit length. In the example in the book. So if this says v of alpha goes around in a circle, v prime of alpha is a vector orthogonal to v of alpha that also rotates around the circle. So as a first example of combining geometry with algebra and accepting geometric vectors on their own terms, let me prove to you that if a vector is constant length, that if some vector as a function of parameter is constant length, then its derivative is orthogonal to the vector itself. Here's how you do it. Right? So it's very nice. So this might be called basic vector calculus. It's combining geometry with calculus. And what we have so far, the elements we have so far, is enough to combine geometry, a little bit of geometry with a little bit of calculus.
Isn't that expression just the partial derivative though? Isn't a vector technically also, you could change the length, keeping the angle constant?
Yeah, see, that's, I understand. So I gave you one parametric family. In my parametric family, the length happened to be constant. So I just gave you this parametric family of vectors. I could have given you this parametric family of vectors. How would I display? Here I could have said the length, it points at the angle alpha, and the length equals alpha. That would be a spiral. Let's call it S for spiral of alpha. I think it may be called the Archimedes spiral. Look, this is another family. For this family, the length and direction change. Yes, both can change. But it just so happens that in the example that I gave you, only the direction was changing and the length was staying constant. But it's still a full derivative because the vector depends only on one parameter, alpha. So your confusion comes from the fact that this parameter also happens to be angle. So you're thinking, well, you're just changing the direction. Yes, that's a special feature of that particular example. You can think of it, maybe it'll be a little easier if you replace it with t. Yeah, but I chose this because I only have geometric vocabulary at my disposal here, so I wanted to choose a family that I could easily describe. Some other families might be harder to describe, so that's a very, very particular one. So the proof that it's the orthogonal vector of the same length, you really want to do that very carefully. Understand that very carefully because it's used, just this particular example is used in a lot of cases. But now I'm doing something almost unrelated to this. I'm saying, look, it's orthogonal. That's very interesting. So I'm going to give you a slight generalization. Not generalization, but insight into why in this example the derivative happened to be orthogonal. And the pattern is that if a vector as a function of the parameter is constant length, then its derivative is orthogonal to the vector itself. And don't necessarily think of the parameter as angle or anything else geometric. So the parameter could be arbitrary. T, it could have just as long as for every value of the parameter that exists somewhere else. T would be time, alpha is angle, it could be anything. But as long as there's a numerical parameter, you can talk about vectors as a function of a parameter. So here's proof. What does it mean that a vector is constant length? That means that if I take the vector as a function of the parameter, so I'm going to use t instead of alpha so you don't think it's angle. But I also don't want you to think of u as velocity. When you see v of t, you might think velocity. So I'm going to take u. U of t. Let's just make it pretty. Oops. Working out this job. U as a function of t dotted with u as a function of t equals constant. Some constant. What should we call it constant? A. Now I'm going to take the derivative of both sides with respect to t. And I will use the product rule on the left-hand side. Now you might ask, so you introduced vectors, great. You introduced the dot product of vectors, that was kind of a strange thing. Length of one times length of the other times the cosine of the angle between them. That's an unusual operation. It's not really a product. It's some other thing that's product-like. Why is the product rule justified, that it satisfies the product rule when you take the derivative of it? Well, it's a very valid question, and it does satisfy it, and we can think about it separately. But it's certainly true that the dot product under the derivative satisfies the product rule. So by the product rule, the derivative of the right-hand side is 0. But the derivative of the left-hand side is du dt dotted with u plus u of t dotted with du dt. And the right-hand side is 0. And because the dot product is symmetric, these two terms are the same. So what I really have written is that 2, but I can cancel the 2. So u prime of t dotted with u of t equals 0. And that tells you that the derivative of the vector is orthogonal to the vector itself. So that's a sort of a very, very basic fact about differentiating vectors. If you're differentiating a vector with respect to any parameter, and that's all you can really differentiate it with respect, it has to be a function of some parameter, then the derivative of a constant length vector is orthogonal to the vector itself. You guys are with me on that? So if you are swinging a big stick, right, and there's something at the tip of a big stick, and you're swinging a big stick, no matter what you do, as long as the base is fixed, the velocity, which is the derivative of the location of the end of the stick, is always orthogonal to the stick itself. Okay, nice. Okay, so that's part of the rule of the game. Part of the rules of the game. We can differentiate vectors with respect to whatever parameter. Okay, let's talk about curves a little bit. Now that we can differentiate vectors, let's talk about differentiating the position vector. So when we have a curve, we're going to parameterize it. What does it mean to parameterize it? It means every point gets assigned a value of the parameter. Let that parameter be, you choose, t or alpha. What are you more comfortable with? Or beta? T? Fine, t. Then you're kind of involuntarily thinking of it as time. That's fine with me. Okay, here is my position vector r. Here's my position vector r. And let's look at the value of the position vector for the points on the curve. Right? That's, wow. So much for the Euclidean space. Still curved?
That's it.
Close enough. So, at every point on the curve, we have a special value of the position vector. So, at that point, I would say that the position vector on this curve is a function of the point. I don't need a parameter. I could say, at this point, here's the position vector. At this point, here's the position vector. At this point, here's the position vector, right? Very factual, tangible, but not, you can't do much math with it. Instead of saying, what's the vector? You say, here it is, right? That's all you can do. You can't do any calculus. But once we assign a parameter to each point on the curve, now the position vector becomes a function of time. Now the position vector becomes a function of time. And when you have something that's a function, not time, parameter t, and now that r is a function of some parameter, so we're going to define arc length. I'll write down an expression that will make intuitive sense, and because it will make intuitive sense, we'll call it the definition of arc length. So arc length, let's call this the point where the value of the parameter is t0. And this would be another point where the value of the parameter is t. So then arc length function of time, is defined as the integral. You have to pick where the point where arc length equals 0. So we're going to say arc length starts here. Depending on where you choose, you'd have a different function, but it'll be just a shift. To t. So instead of saying dr dt, I'll just use shorter notation, r prime. R prime of t dotted with r prime of t all under square root dt. So I think it corresponds to your intuitive understanding of what length is, because r prime of t is the velocity. If you think of t really as time, then r prime of t is velocity. Velocity dotted with itself is the absolute value of the velocity squared, speed squared. So when you take the square root, you just get speed. So I'm just integrating speed with respect to time. So of course it's the distance covered. Right? So it makes intuitive sense. It makes intuitive sense. But other than that, it's not justified, other than the fact that it makes intuitive sense. But it's good enough to say that's the arc length. And to be totally clean, people put star here. Well, we already used star, so we have to put, like, I'll put a literal star in here. So you do that to distinguish it from this t, right, or else they get mixed together. That's just the integration variable. So that's my definition of arc length. And it's all concepts. We're building it up all just from concepts of length, angle, dot product, taking derivatives of vectors, followed from that. I remembered now what I wanted to say about the inner product. Maybe I'll say it at the end. Well, let me say it now. Let me get back to that. Very important. U dotted with V equals the length of U equals the length of U times the length of V times the cosine of the angle between them. And the difference from linear algebra. In physics, in vector calculus, geometry, and tensor calculus, the primary concept is length. And if you need angle. And from the concepts of length and angle, by putting together this combination, we can define in the inner product. And then the fact that the length, that the inner product of a vector with itself equals its length squared is just a consequence of the definition. In linear algebra, the expressions look the same, but the logic is completely different. The inner product is the primary concept. The inner product is defined in a very abstract way as a bilinear function that's positive definite. That's the definition of the inner product in linear algebra. From that, this length of one times length of the other times the cosine of the angle between them is just one of the examples of the inner product. But in fact, length in linear algebra comes from the inner product. You define the length of a vector as inner product with itself under square root. Here, it's opposite. Length comes first, and from length you build up the inner product, as opposed to linear algebra where the inner product comes first, and from the inner product you build the concept of length, and you build the concept of angle. Right, so very different in terms of how the world gets built up. Okay, but here we see everything is from our primary notions. We have our vectors, which are pointed arrows. We know how to take derivatives of them. We know how to dot them. Now we just have a scalar from which we can take the square root just because it's a number. We can take square root of numbers and then integrate numbers, functions that have scalar values. So all of it is built up from our primary concepts. And we can use the fundamental theorem of calculus. Let me take the derivative of s of t as a function of time. So that's the rate of change of arc length as a function of time. And of course, it is s prime of t equals square root of r prime of alpha dotted with r prime of alpha. Ooh, went from t to alpha of t. Let me show you from this and complete this thought one fantastic consequence of this. What I didn't mention is that another thing that makes this integral valid, I think it's one of the exercises in the book, is that if you went from one parameter to another, from t to alpha, if you reparametrize this curve and evaluated this integral again, changing the limits appropriately, you would get the exact same value. Intuitively speaking, if you reparametrize it, that means you travel it faster or slower. So at each point, let's say you reparametrize it, it's hard to say the word, reparametrize it, so that you cover the whole curve in half the time. That means you move twice as fast. And when you recalculate everything, you'll realize that this derivative is twice as large. So your integrand is twice as large. Well, let's see. This is twice as large, this is twice as large. You multiply them together, it becomes 4 times as large. You take the square root, goes back to being twice as large. So your integrand is twice as large, but your range is twice as small. So in combination, you get the same value. So it's kind of intuitive, although it can be easily shown. If it's not an exercise in the book, it should be. That this integral is independent of parametrization under certain reasonable conditions. So where was I taking this? So as a parameter itself, how about this for a parameter? It's used very frequently. It's used so frequently I would say it's overused. Let's use arc length as the parameter. Does that make sense? I will label the points on the curve according to how far away it is from some starting point. So I'm now going to use S as the parameter. I'm going to use S as the parameter. So this would be where S equals 0, or some value S0 from which we're starting. Right? And all the points are now labeled by how far along the arc they are from this point. So now my parameter T is S. This would still hold. This is general. This is for any T. So let's see what we get if our T is the parameter S. Well, we know what S as a function of S is. It's S. That's like the easiest function. What is arc length as a function of arc length? It's arc length itself. S as a function of S is S. So this derivative is 1. So we'll have 1 equals square root of r prime S dotted with r prime S. So I think all of these things are simple, but just take time getting used to. Okay, I'm finally beginning to get used to this chop. So what is this saying? What this is saying is that if arc length is used as a parameter, don't be put off if this is a little hard to wrap your mind around, all of these things. We'll be doing these so often that you'll come back to this and you'll be totally used to it. That when the arc length is the parameter, then the derivative of the position vector with respect to arc length is not only a tangent vector, but, can you complete the sentence? What is this saying about? It's the unit tangent vector. So you always get the tangent vector. But if your parameter is arc length, then it becomes the unit tangent vector. So we'll use this over and over again. In fact, this could be used as an alternative definition of arc length. It's that special parameter such that the derivative of the position vector with respect to it is the unit vector. You always get tangent, that sort of definition, but you get the unit vector.